Okay, so who hasn't wished they could just teleport somewhere, right? I mean, skip the lines, the traffic, the whole travel hassle, and just poof, you're there.
Yeah, it's a classic for a reason. Beaming ourselves up is still, well, science fiction, but teleporting information. That's something scientists are actually working on.
Seriously, like sending emails without the internet, how does that even
It's
work?
not quite that simple, but you're on the right track. We're diving into quantum teleportation today.
Okay, gotta admit, that definitely has my attention.
We've got a research paper. It's fascinating, and it takes us from these theoretical simulations to actually testing this on an IBM quantum computer.
All right, color me intrigued, but before we go any further, for those of us who haven't quite, cracked the quantum code yet, what exactly is quantum teleportation?
That is the question, isn't it? And it's not about, like, physically moving particles Star Trek style. Imagine you want to send someone a recipe. Quantum teleportation is like sending the instructions, not the actual ingredients. You're recreating the information at the other end using this really cool thing called entanglement.
Okay, entanglement, that's where two particles are linked together, right?
Yeah,
Even if they're miles apart, they still act like they're connected.
you got it. It's like they have this invisible string between them.
Yeah.
So in this paper, the researchers, they used 3 of these quantum bits, qubits they're called.
3 qubits. So like digital triplets or something?
Exactly. One qubit holds the information that they want to teleport, and then the other 2, well, these are the real stars of the show, they form something called an EPR pair. And this pair, it's entangled. So they're linked in a way that lets them share information instantly. Doesn't matter how far apart they are, that's the quantum magic that makes teleportation possible.
Okay, so we've got our qubit triplets. One's got the data, the others are our entangled superstars. What happens next?
All right, so this is where it gets really interesting. The scientists, they ran this experiment, both as a simulation and on an actual IBM quantum computer. And just to make sure they had enough data to really analyze, they ran a crazy 892 shots.
Hold on, 892 times? That's a lot of shots.
Yeah.
So did it work? After all that, were they able to actually teleport information?
So that's the thing. Both the simulation and the real quantum computer, they showed signs that, yes, teleportation was happening, but, and this is a big but, there were some interesting differences.
Okay, now you have to tell me about these differences. What are we talking about here?
Well, the paper, it specifically talks about the distribution of possible quantum states in the results.
Distribution of quantum states. I'll be honest, that sounds a little over my head. Can you break that down a bit?
Sure, think about it like this. Imagine you're sending a message, but it's written in some kind of secret code. This distribution of quantum states, it's like checking to see if all the letters in your message arrived in the right order.
So they were checking to make sure the information, once it was teleported, that it all arrived in one piece.
Exactly. And what's amazing, they found that this distribution was pretty even, which is what you'd expect if the teleportation worked. Like the message got delivered, even if the journey itself was a little bumpy.
Bumpy how? Did something go wrong?
Well, remember how I said there are these interesting differences between the simulation and the actual quantum computer?
Yeah. Yeah, so the simulation, it was like clockwork, perfect information transfer every single time. But the real IBM quantum computer, it still showed success, but there was definitely more variation in the results.
So what caused that? Like, was it just a glitch, or is there something more going on here?
That's the million-dollar question, and it takes us to one of the biggest things that's slowing quantum computing down, this thing called quantum noise.
Quantum noise. Is that kind of like when, my headphones are plugged in, but I can still hear this, like, static in the background? You're getting it. Think of it like static on a phone line, but instead of messing up your music, it's messing with our quantum information, right? It can even lead to errors in this thing called decoherence.
Decoherence. Okay, now that one sounds a little intimidating, I'm not going to lie. What does that even do?
Imagine you've got a photograph, right? And over time, it starts to fade. That's kind of what decoherence does to quantum information. Makes it fuzzy, less defined, harder to read, basically. And that's a major hurdle in making these quantum technologies reliable and scalable to actually use.
So it's not that the information is just gone. It's more like it's getting garbled when we try to send it, like trying to have a conversation in a hurricane or something.
There you go. That's a great way to put it. And this is what this paper is really highlighting, how important it is to solve this challenge of quantum noise. I mean, if we want to build these really sophisticated quantum computers, the simulation, because it's this perfect world, no noise, it was flawless teleportation every time. But the real IBM quantum computer, it's impressive, but it still has to deal with the noise of, the real world.
So this isn't about like the experiment failing. This is about us understanding the limits of where this technology is at right now. We're basically getting a backstage pass to how messy, but also how cool this cutting edge research is.
Exactly. And we can't forget we are in the very early stages of this whole thing. It's like it's the Wild West out there, you know? Breakthroughs and challenges around every corner.
Makes you wonder if they need a quantum sheriff or something. But speaking of keeping things in order, the paper also mentions simulations, right? Like how important those are.
Absolutely. Simulations are huge for these researchers because it gives them that controlled environment where they can design and test these quantum circuits without that real-world noise messing things up.
So it's like a testing ground, work out the kinks before you launch the rocket into the chaos of quantum mechanics.
Perfect analogy. And what's really cool is this paper, it shows that these simulations are surprisingly accurate even when you compare them to the real IBM quantum computer.
So it's like a good roadmap, even if there might be some detours along the way, thanks to things like, oh, I don't know, quantum noise.
Exactly. And that kind of validation is massive, right? It means researchers can be more confident in their designs, even with the errors that come with today's hardware.
Okay, so we've talked about the potential, we've talked about the challenges, how good these simulations are, but like, what's the point? Why should our listeners care about these entangled qubits? What's the so what here?
That is the question, isn't it? This research, it's like a little window into this future where we might be able to do some really incredible things with this quantum information.
So we're not just talking faster computers, we're talking like a whole new internet almost. But right now, it kind of sounds like we're sending smoke signals in a windstorm with all this quantum noise.
It's a challenge, yeah, definitely, but not one we can't overcome. I mean, think about it. The early days of computers, regular computers, they were full of errors too, right? But we figured out ways to correct them, make them more reliable, and that's exactly what's happening now in quantum computing.
So we need to like debug quantum teleportation. What's the plan?
Researchers, they're coming up with some really clever stuff, I gotta say. New quantum algorithms, which are kind of like the instruction manuals for these quantum computers and these error correction codes, they help clean up the noise, so to speak, and make that information transfer way more reliable.
So like a signal booster, but for quantum information.
Exactly.
Yeah.
And the coolest part, this isn't just some computer science problem. This is pushing the boundaries of physics, engineering, even math. It's pretty amazing what we can do when we put our minds to it.
It really is. Makes you appreciate those folks who are out there trying to, herd quantum cats or whatever. But all jokes aside, for those of us who aren't quantum physicists, how could this impact, everyday life? It all sounds pretty complex.
It does. But the potential here is huge. Imagine like personalized medicine,
Hmm.
designed for your specific genes,
Mm-hmm.
or ultra-efficient renewable energy, or even, get this, communication networks that are basically unhackable. And that's just scratching the surface.
Okay, now you're talking. Sign me up for the unhackable internet. But really, it's like we're getting a glimpse into the future and it's straight out of sci-fi.
And the best part is we are just getting started, really. This paper, this research on quantum teleportation, it's just one piece of a much bigger puzzle.
It's like we've just flicked on the lights in this giant room and we're starting to see how much more there is to explore. So for our listeners who are now hopefully just as fascinated by all of this as we are, what's the one thing you really want them to walk away with? What's the biggest takeaway from our deep dive into quantum teleportation?
Good question. I think it's this. We always hear teleportation and we think sci-fi, right? But the reality, it's much more profound than that. What this research shows us is that teleportation, well, at least on the quantum level, it's not just fantasy anymore. It's a glimpse into this future where we might actually be able to use these honestly kind of bizarre rules of quantum mechanics to do things that, well, we thought were impossible.
It's a good reminder that the future is full of surprises, and that sometimes the most groundbreaking discoveries, they come from exploring the things that at first seem impossible. And on that note, I think this deep dive has given us all a lot to think about. So until next time, stay curious, everyone, and remember, even the most mind-boggling ideas, well, they might be closer than we think.